So let's just pull this up. If you look on Canvas in the newly created Exam3 folder, there's a long document that includes a bunch of review problems. What I can do is I was just going to pick a couple of them and go through the review problems here. I think we probably have time to get through at least one, maybe two. And then I can answer your questions on that. I've posted both the review problems and the solutions. This is a set of problems that I didn't create and I didn't write the solution for, but I have. So I've posted them. I haven't verified that there's no typos or anything like that, but I trust the source and I think they're pretty good. So hopefully that will be useful to you. If you have questions on it, Piazza is a great place to post on that, or send me an email and let me know. But what I want to do is just go through a heat exchanger example and or a radiosity example. So let me just get a sense, who would rather I go, of the two, who would rather I go through the radiosity problem? Okay, and heat exchanger problem? Heat exchanger, okay. We'll do the heat exchanger one first, and if we get to the radiosity, we'll do that. And again, stop me if you have questions on this, okay? Okay, so this problem is looking at a parallel flow heat exchanger, a parallel flow. So we're dealing with flow in this direction, flow in this direction. The heat exchanger is being used to heat air, and then it's using water, so it gives some temperatures. Things that it points out. So the capacitance rate of air is 0.1 watts per Kelvin. The capacitance rate of water is 10. And then it gives us the conductance. Okay, so right away, what do we know about this problem? Right away, we know there's a big mismatch between the capacitance rates. All right, 0.1 to 10 is 2 orders of magnitude. So there's a big difference there. That's going to affect the behavior. The other thing that we know is that we're given the conductance. So if you saw this and your first instinct was, well, I got to start computing resistances, I need to figure out the convection coefficient and so on, right? That is not the right response. You're already told something about the conductance. So unless we're later asked to compute some part of that, you don't need to deal with it, right? We're sort of past the point of needing to know detailed geometry for this. Okay, so what it's asking then is, let's sketch the temperature distributions in the heat exchanger. So that is the temperature in the water is a function of x. Make sure that the qualitative features are correct based on the operating conditions. Okay, so what I'm going to do is I'll just create a little plot here, kind of notate it. So we have position x. We are told that we have some T water. So this is T water in, and that is, I think, 80 degrees Celsius. We have T air in, and that is 10 degrees Celsius. So let's say that's down here. And we need to plot the temperature profiles. Okay, so first, let's remind ourselves. So, okay, so air has 0.1, water has 10. So which of these two fluid streams is going to change temperature more? Air or water? Any guesses? Air, right? Lower capacitance rate means it can tolerate less heat input for a given increase in temperature. Okay, so air is going to change less, and how much less is it going to change? 2 orders of magnitude less, okay? So let's say qualitatively, I'm not going to even bother calculating what the performance is of the heat exchanger. Qualitatively, I know, let's say air is doing this, right? Let me just do it correctly here. Air is doing this. What is water going to do? Water is going to change by 2 orders of magnitude less, right? So it can barely even pick it up. So this would be like going across here. All right, and again, this is parallel. So you might ask, why did I draw it like this as opposed to like this, right? Why did I draw the water temperature decreasing and the air temperature increasing as opposed to water temperature starting low and going high? It's because it's parallel flow, right? Parallel flow. They're both coming in the same direction. Hopefully that makes sense. Now, if I was like being really picky about this, or if you're a little confused about it, you can also realize that the heat transfer rate, the local heat transfer rate, is actually dependent on the temperature difference. So what we're drawing here, these like straight lines, is implying that there's a constant heat transfer rate as a function of position. But that's not quite right, right? So like you could also draw it like this, right? Where there's sort of like, there's sort of a dependence on position. You know what I mean? Like, so like there's a really steeper increase. Come on, there's a steeper increase here than there is here, because there's a larger temperature difference at the inlet. The solution in the exam folder gives it with straight lines. I don't really like that. I mean, I'd prefer that you actually capture the fact that there's a dependence, but that's where that comes from. Okay, so that was part A. We can go on to part B. Here I've included in my blank the answer. So part B says determine the heat transfer rate in the heat exchanger as well as the temperature of the air leaving the heat exchanger. So determine the heat transfer rate in the heat exchanger. So how are we going to approach this? I guess we're only given the inlet temperature conditions. Yeah, question.
If we're asked to draw that on exam, would points be awarded to straight lines?
Yeah, that's a question. I was hoping nobody would ask that. The question was, if we drew straight lines, would you give full points? I would say probably yes, I probably would. This case is a little bit egregious because like it's really changing. So I didn't even draw it like that great, but it's really going to be looking like this, right? So I don't know. I would say probably yes, I would give you full points, but you should realize or should at least understand the fact that the local heat transfer rate is related to local temperature differences. Okay. Did I answer your question? I don't think I did. Do I have to answer it? Yeah. Other questions? Yeah. Do you have a question? Okay. Okay. So then part B, we are now asked to compute things. So what we need to realize here is like what information do we have? And then what do we need to get? So we're given conductance, we're given inlet temperatures, we're not given like a heat transfer rate, we are given capacitance rate. So somehow we need to realize that, okay, I need to involve the effectiveness in some way. The effectiveness equations have to play a part in computing this because I just don't have enough to do this solely on an energy balance basis. Like there's nowhere I can just compute Q dot from the conditions of the flow streams. So once we realize that we have to use effectiveness, the first step is going to be what do I have, right? And then how do I get to effectiveness? So I know I'm given UA, conductance, right? We're given that. I'm also given the capacitance rates, so C dot H, and I'm given C dot C. Okay. From that, I know I could also compute capacitance ratio. Okay, so from this, my first step is going to be NTU. I'm going to use my relationship for NTU. So we'll say NTU is equal to UA, conductance, over C dot min. Okay, so I can plug in values. This would be 0.1 for conductance divided by C dot min. So C dot min, there was 10 and 0.1. So it's going to be 0.1. So this is 1. My NTU is 1. Okay, once I have an NTU of 1, let's see, from that, maybe we can also compute the capacitance ratio while we're at it, so CR. And so this is C dot min over C dot max, which is 0.1 over 10, which is 0.01. Okay. So now what can I do? Well, at this point you could say, well, I'm going to go to look at effectiveness relationship, but we actually don't need to do that quite yet. So we can use our definition of the maximum heat transfer rate and sort of go that route. So if we said Q dot max, right? Q dot max, that's going to be C dot min times T water in minus T air in. That is 0.1 times 80 minus 10. And that equals 7 watts. So I know the maximum amount of energy that I could transfer. All right, so now at this point, I can go look for effectiveness. So effectiveness, what I would need to do is pull up like the relationship. I don't have it in the solution here, but basically you go to the table that's parallel flow. So this would be like parallel flow. And plug in your information that you have here, and from this you would get an effectiveness of 0.64. Right, so this comes from effectiveness as a function of NTU and capacitance ratio. Right, so that's where we're getting it. You just plug it into the equation. So we get 0.64. Okay, from that, then we say Q dot, the actual heat transfer across this, is equal to effectiveness times Q dot max. Because remember, I don't know, draw it over here, but effectiveness is defined as Q dot over Q dot max. All right, so then we plug in our values here. So this is 0.64 times 7.0. So this is 4.48 watts. All right, so that is, let's see, determine the heat transfer rate, so that's 1. Note, I am putting a box around my final answer. Please remember to do that. We're also asked to compute the air temperature. So now I can do an energy balance, right? So T A out is equal to T A in plus Q dot over C dot A. This is just an energy balance on the air fluid stream. So this is 10C plus 4.48 over 0.1 equals 54.8 degrees C. Okay? So that, I think, answers that part of the problem. Any questions on that? Half the battle with the heat exchanger problems is knowing where to go, right? Like, what information do I have? What do I need to get? You need to sort of get all the pieces of information, effectiveness, conductance, maybe total resistance to get to conductance, the energy balance pieces, right? You have to kind of sort out what it is that you need that's left that you need to figure out in order to compute the remaining equations. Okay, let's see if there's anything else to talk through here. Yeah, okay, so the sketch, you can look in the solution, but this is just saying sketch the rate of heat transfer as a function of conductance. So this, I guess I left the solution in here, but it looks like this. Let me skip to this part here. I didn't even leave space for it. Yeah, okay. So this is just a conceptual, okay. First of all, let me just say, like, I had the full solution. I did not have the blank document, so when I went through, I just cut out all the stuff that hopefully gave you a blank document. I clearly didn't do that very thoroughly, because here's the answer for part D. But just so if you're confused when you're looking at it. Okay, part D is asking, your boss has heard that it's always better to do a counterflow as opposed to parallel flow, insists you replummet. Can you justify like why it doesn't matter or why it does matter? So I think to answer this one, right, all they're saying is he's insisting you do it this way as opposed to parallel flow like we had originally done. Why does it not matter in this case? Right? Why does it not matter? Well, it's because my capacitance ratio is basically 0, right? I've got 0.1 over 10. That's a capacitance ratio of 0.01. That's pretty close to 0. So if you remember, if you look back at, I guess I don't have it on this slide, but if you look back at the performance as capacitance ratio goes to 0. Remember, configuration doesn't matter in that case. So here, what we're saying is, I guess we can look back at this temperature plot. Right here, what we're saying is, I've plumbed it this way. The total heat transfer in this device is related to like the total temperature difference between these two fluid streams. If we were to have reversed it, it would look like this. That total temperature difference is pretty much the same, right? So it just doesn't matter. So you basically have to explain that, and that's basically the answer there. Okay, well, that's as far as I got. Well, let me just say thank you all for being in the class this semester. I've enjoyed getting to know a lot of you. Thank you for your attention, and good luck on the final. Thanks.